or counterintuitive behavior. And it's your job as the audience to guess what the program does. So we'll poll you after showing the program. You will tell us what it does by show of hands, multiple choice, typically 4 choices. And then we reveal the mystery. But it's not all fun and games. With each of these puzzles is a moral. And the moral tells you how to avoid whatever trap or pitfall was displayed in that particular program. Typically, in these puzzles presentations, we've discussed only the language and the core libraries, mainly java.lang and java.util.
But since I'm a special guest, we're actually going to be throwing a few new things into the mix, and you'll see them as we get to them.
Excellent. Why don't you give me the first one?
Okay, so I've got a puzzle for you, the joy of sets. So we're going to take a set and add things to it and remove things from it. And at the end, we ask, how big is the set?
Okay.
And the question is, what does this program print?
Well, this doesn't look too hard. At least it's short. In fact, it's a set of shorts. And let's see. We initialize it to a new hash set of shorts. That's kind of the basic set implementation. And this is the sort of the idiomatically correct way to do it, where the type on the left-hand side is set, on the right-hand side the implementation type. We iterate for I starts at 0 and goes all the way up to 100, actually 99, because it's I less than 100. And then we add that element to the set. So first we add 0, and we remove I minus 1. So I guess that's like the previous element. In the first case, we're going to try to remove -1. Now the set doesn't contain -1, so that's a no-op. Second time through the loop, we add 1 and remove 0, leaving 1 in the loop. Next time, we add 2 and remove 1, leaving 2. So each time through the loop, we only have the most recently added element.
Mom always said to clean up after ourselves.
Yes, that appears to be what we're doing here. So after the 99th iteration, the set contains 99 and no other elements. What we're printing is the size of the set, which is 1. So I would have to say this program prints 1.
Well, let's see if that's one of the options. Yes, indeed it is. And the question is, does this program print 1, 100, does it throw an exception, or none of the above?
And that could mean, that it varies from run to run, but there's one thing it could not mean.
Yes, that's right. So sometimes in the past, we've had Java puzzlers that don't compile.
And we have found that the audience gets very, very angry when this happens. So this year, we make you a pledge. Space Cadets Honor.
Space Cadets Honor.
All of the
puzzlers
programs compile.
So, yes. So, now it's time for you guys to decide, does this program print 1, 100, throw an exception, or do something else? Right? And you're all required to vote. This is not something where you're allowed to simply sit on your hands. Right? It's okay to be wrong. Many people are. Okay. We think we're ready.
We're ready.
All right. So, how many people think, the answer is A, that this program prints 1? Okay. How many people think that this program prints 100? B. Okay. How many people think that it throws an exception? Okay. And how many people think that the answer is D, none of the above? Okay, I'd say that was about evenly split between A, B, and C, roughly.
Yeah, I would say so. Well, let's find out what it really does, shall we?
Okay, so what does it actually do? It prints 100.
100?
Yes.
Well, why does it do that? It removes all those elements.
The problem is that it adds shorts to the set, but it removes integers.
It removes integers. Let me take another look at this.
Okay. So the problem here is that I minus 1 is an int valued expression.
Oh, wait a minute. I is short and 1 is a little tiny number. Why is it?
But whenever you perform any sort of arithmetic operation on anything that could be an int, then the result is either an int or possibly a long if you're working with long. But any sort of combination involving shorts, bytes, or anything, any sort of integer operation with that produces something of type int. And so this int computation is going to get auto-boxed into an integer object. And the short that contains the value 1 and the integer containing the value 1 are actually distinct objects that do not compare as equal. And thus, if you have a set that contains the short 1 and remove the integer 1, it is a no-op.
Well, that's all well and good, Bill, but wasn't set parameterized, that is generified in 1.5?
Yes, it was. It was generified in 1.5, and you can see we defined this as a set of short.
But shouldn't the compiler complain when you try to remove an integer from a set of shorts?
You might think so, and you would be wrong. Right?
Dang.
So it turns out that for the set, if you try to add something to a set of short, the compiler enforces the restriction that you can only add a short. However, the remove method for a set of E allows you to remove anything from it. You can remove a string buffer, you can remove a string, you can remove anything you want.
But isn't that a bug if you try to remove the wrong kind of thing from a set?
Well, it's type safe. Right?
Okay.
And to some extent, that was one of the things that designed how things got generified. It turns out that there are some cases in which you might want to iterate through a collection of objects and remove everything in that collection of objects from the collection of shorts. And in order to maximize backwards compatibility, it was decided that there are a number of methods, such as the remove, also very important, the get method on a map, where the type of the parameter is object. If you have a map from strings to strings and pass it a string buffer with get, that will compile and it will return null because there are no string buffers in a map from strings to strings.
In fact, by the way, when we were generifying the collections libraries, we first attempted to enforce that restriction, and we found that it simply didn't work. There were many reasonable programs that just could not be generified if you were only allowed to remove a T from a collection of Ts. For example, suppose you want to intersect a list of numbers with a list of longs. That's perfectly reasonable. You know, you're kind of going to take out all the longs or you know, get all the longs from the list of numbers. It should compile, and it does. Great. So what can we? How do we fix this one?
Well, one way you can do it is you can cast this result back to a short, a primitive short, and then this will get auto-boxed into a short object, and therefore the short object, the short 1 will find the matching short 1, and you'll actually remove the object that you'd added to the set in the previous iteration.
And so then the program would print 1.
Then it will print 1.
And my answer would be correct.
Yes, it would.
Great.
Once the program is fixed. Yes.
And what can we learn from this one?
All right. So first off, that there are a number of methods in the collection classes that even when you supply generic types, they take objects as parameters, and you have to watch for these. So the remove method takes object map.get and so forth. You just have to be careful about that. Integral arithmetic, any math operation involving any sort of integer value results in always an int or a long, never a byte, a short, or a character.
And what that means, by the way, is that byte, short, and char are sort of inferior types. You can have things of that type, but once you operate on them, they always turn into ints.
So avoid mixing types. You know, ints and shorts, that can bite you in a number of ways.
Is that a pun?
Yes. And avoid short, avoid int, you know, prefer int and long. Basically, the only really compelling application for shorts in your programs is if you want to have a very large array of shorts. You really buy absolutely nothing by having local variables or fields of type short. It doesn't get you anything other than confusion.
And by very large, I think Bill means very, very large. Because, you know, suppose you've got, say, 1 million shorts. Is that large? Well, you know, I guess each short is 2 bytes, so 1 million shorts is 2 megabytes. But I don't know about you, I buy my memory in gigabytes these days.
Some people run Java on small platforms.
Oh yeah, that's true. So those people should worry about it. Okay, so that was a great problem, Bill, but now I have one for you.
All right.
Yours was the joy of sets, mine is more joy of sets.
Okay.
And yours, well, mine is sort of superficially similar to yours. Yours considered sets of shorts. Mine considers it sets of URLs. So what we do is we have a list of strings. They are my favorite URLs. And we make a hash set we put the URLs into it, and then we print the size. So my question is simple. What does this program print?
And why are we so preoccupied with size? Okay.
Good question.
So what does this program do? We've got an array that's going to be initialized to contain 6 different strings. Java Puzzlers, Apache 2 Snort Skybar.
Yes, Snort. It's the best.
Ah, okay. Yeah, Josh has some interesting favorites. Google Java Puzzlers. Now that's a repeat of this one. The FindBugs website and the University of Maryland website. Okay, so we've got these. We get into main, and we create a set of URLs. And initialize with a hash set. Then we go through all of these URL names, which are strings. And so for each string, we create a URL object. And we add that to the set. And then at the end, we print out what the size of the favorites are. Okay, so there are 6 strings, but there are only 5 unique ones. Right? And so I'm going to guess that this program create 5 URLs, and when you put things into a hash set, duplicates find themselves. So I'm going to guess that the answer is 5.
5. That's a reasonable guess. Let's see if it's one of your choices. Yes, your choices are 4, 5, and 6. And of course, the ever popular none of the above, which, as I remind you, could mean a different number, could mean throws an exception, could mean varies from run to run. It could mean all sorts of things. So, audience, how many of you think this program prints? Choice A, 4.
We give them a little bit more of a moment to think about it. You guys ready?
That's not a hard problem.
All right.
Nobody for 4. How many for choice B, 5? Wasn't that your choice?
Yeah, that's my choice.
Got about 5 of you. How many people for choice C? 6. Ah, the great bulk of you. And finally, choice D, the ever popular none of the above. A smattering. But this is a clear win for choice C, 6. Then let us see what this program actually does, shall we? Well, as a practical matter, it does print 4. If you run this on 4, if you run this, it will print 4 if you are connected to the net. And you Googlers are always connected to the net. So it will print 4. If you look in the specification, you'll find that the answer is it varies from run to run. And as for the intuition,
how is that possible?
URLs, equals, and hash code methods are completely screwed up. It's as simple as that. Let's take a closer look. Here's the deal. These 2 URLs may be different, javapuzzlers.com and Apache Snort Skybar dreamhost.com, but they resolve to the same IP address. And so, from the perspective of the marvelous and magnificent URL class, they are equal. If you look at the specification, you will find out that 2 URL objects are equal if they reference equivalent hosts. And furthermore, 2 hosts are considered equivalent if both host names can be resolved to the same IP address. And the other kind of interesting factoid here is that since host comparison requires name resolution, checking if 2 URLs are equal can block. Is that not delightful?
But, I mean, so Apache 2 Snort and Java Puzzlers, if you actually go there in a web browser, you see entirely different websites.
Yeah, they call that virtual hosting. And it turns out that the equals method for URL is incompatible with virtual hosting. Because, when URL was added to the platform, which was like 1993, there wasn't a lot of virtual hosting going on. Those were kind of the early days of the web. So how do we fix this one? Well, it's really easy. URL is broken, so don't use it. Use URI instead, which is a newer class and much better designed. It turns out that the equals method for URI is kind of structural. It's just based on the text here. It does a little bit of canonicalization. So for example, it strips out extra spaces and so forth. I think it might even do capitalization. Does it? I'm not sure. But anyway, it is well specified, and it does the right thing. So if you run the same program using URIs instead of URLs, it will print out 5. because of the fact that Java Puzzlers is on the list twice, so it is equal to itself, but the others are all distinct, even though two happen to resolve to the same IP address. Notice, by the way, that instead of calling a constructor, we have a static factory here, because it turns out that static factories are just generally better things than constructors, and since this is a later class, they added a nice static factory to it. So use it. And what can we learn from this one? Well, the main thing that we can learn is because URLs are broken, you should not use them as set elements or map keys. In fact, you pretty much shouldn't use them much at all. It turns out that their equals and hash code methods simply aren't well defined, and they disobey the general contracts for equals and hash code. One of the contract stipulations says that the equality and the hash code of elements should not change over time unless you change the elements. But in this case, whether or not you're connected to the network can change the behavior of your program. So if you experience an intermittent web connection failure, but that never happens to you guys, right? But if you do, the hash code of your object can change. Isn't that horrible?
Well, I could also imagine at Google, you guys might create some large hash maps of URLs. And that could create a serious network load when you're trying to do some tests or stuff.
It's true. So just don't use URLs as set elements or map keys. Use URIs instead. And if you need to have a URL because some other API requires it, simply call the method that allows you to view a URI as a URL. And the general message for API designers here is that your equals method should never depend on the environment. When you're checking if two objects are equal, it should involve quick tests of in-memory objects. Simple as that.
All right. Well, that was a good puzzle. Now I have one for you. A racy little number.
Ooh.
So we're introducing some new things here, which I think have never been seen in a puzzler before. JUnit and concurrency. So we're basically going to create a test case in which we create a thread which is going to check that a number is equal to 2, and we're going to set the number, start the thread, increment it, join. I'll let you work it out.
Okay, well, let's take a look at it. So let me see. We have a single test method. By the way, I don't see any print statements, so what am I supposed to tell you here?
Well, okay, so this is JUnit, and JUnit doesn't depend on print statements. Rather, you write methods, test methods, that throw an exception if something goes wrong.
So you want to know if the test passes or fails.
Right.
Well, why didn't you ask me that?
Right. And so the question is, does this test case pass or fail?
Okay, let's take a look at it then. So we set number to 0. We create a new thread whose run method invokes the runnable, whose run method is just asserts that the number is equal to 2. So the question is, will the thread see number as 2 or some other value? If it is 2, the test passes. And if it's some other value, it fails.
Right.
So let's see. We start out with the number 1. Then we start the thread. Then we increment the number. And finally, we wait for the thread to complete.
Right.
Now, the thing is that when you start a thread, it doesn't necessarily start right away. So although this number is actually after the start method, I think the number could get incremented to 2 before the thread actually runs. So as a practical matter, I think this program will always, the number will be equal to 2 by here. So the assertion is going to succeed. And I think that the test will always pass. I think the assertion is true.
Let's see if that's one of the options. So the question is, does this JUnit test always fail, sometimes pass, always pass, or always hangs? You know, concurrency. Always got to worry about hanging. All right. So fail, sometimes pass, sometimes fail, always pass, or it always hangs. Give yourselves a moment. Okay, how many people think that this test case always fails? Okay, good number. How many people think that it sometimes passes and sometimes fails? Okay. How many people think that it always passes? Okay. And how many people think that it always hangs? All right.
So that looks like a clear win for B.
Yep. So let's see what this program does in fact do. It always passes
I got
and
it
tells
right.
us nothing. Yes, you got it right. Okay. The problem is that JUnit doesn't get to see whether or not the assertion fails.
It doesn't
Take
get
another
to see
look.
it.
Let's take a look at that code. Okay. JUnit reports that a test method fails if the test method throws an exception, right? And these assert equals methods test a condition, and if the condition is fail, the call to assert equals throws an exception. The problem is that this assert equals isn't occurring in the same thread that invoked the test method. And thus what will happen is that this exception will simply propagate to the top of the stack and then get printed on the console. But the JUnit test harness will see that the test method returns normally and will report a little green dot saying that your test method passed every single time.
Well, that's terrible. So you're saying that the test method will always succeed whether or not the test succeeds.
Whether or not the assertion passes or fails, the test method will always succeed.
Okay.
Now, it turns out that the assertion will sometimes pass and sometimes fail. So those of you who had that intuition, we're halfway there.
There was a little clue in the puzzle that was called a racy little number because it is, in fact, a race condition. So how do we fix this travesty?
Okay, well, unfortunately, this is not one of those one-line fixes. The problem is that what you need to do is if in JUnit you need to start any threads and you want to report an exception thrown in those threads as a failure, you need to have some way to get the exception propagated back to the right guy. And so we're just going to declare fields that will declare an exception or error if they're thrown. And then in the teardown method for the test, we'll check if either of those are non-nil. And basically, all the threads we're going to start, if an exception occurs, they'll shove it into those fields. And then the teardown method will basically check, was an error or exception thrown by any of the threads that we started. So this is sort of what we set up outside. And then in each individual test method, we need to do something else. Next slide, please. And then here, we basically need to, in a run method, we need to catch any exceptions that wind up occurring and store them so that when the main thread, the thread that called the test method, will also be the one that calls the teardown method, these these exceptions will wind up being propagated into that thread, and therefore JUnit will see it and it will get reported. Okay. I have a question.
Is there a reason not to just use throwable as opposed to using error and exception right there?
The reason is that then you would have to go back to the teardown slide.
And yes, the question, by the way, for our viewers is why didn't we use throwable? Why do we have two fields, one an exception, the other an error? And while you're at it, you might as well answer why they're volatile.
Okay. So the reason is that this way we can declare teardown as throwing an exception. In general, I dislike declaring methods that throw throwable. And there are weird things like you can declare things that are throwable that are neither exceptions nor errors and so forth. These are volatile partially because I'm a little bit over conservative. This is a field that could potentially be updated simultaneously by multiple threads, right? And thus, whenever you have a field which could be simultaneously touched by multiple threads, and at least one of those updates is a write, make it volatile. In this case, two people competing to store different values, it probably wouldn't actually impact anything, but better be safe.
Wise advice. Okay, so now that we know how to fix it, what can we learn from it?
Okay, so basically, JUnit does not support test cases in which multiple threads have to coordinate. If you want to do that and want to get errors reported back from any of the threads you create, you have to roll your own or find somebody else who's already rolled one. Okay.
And perhaps the scariest part of it is it gives you a false sense of security. You can write something that looks like it ought to fail, but if it fails in the wrong thread, you'll never see the failure. Please hold your questions till the end of the talk, just because it's kind of a long talk, but do remember them and we will answer them. Okay, so that was a fine puzzle, and now I have one for you. Just a moment. Here, this one. Well, sartorial effect. Because this one's about Elvis. It's called Elvis Lives Again. People who have been to our presentations before know that we have a thing for Elvis. Because Elvis is a singleton. There's only one of him. So, in this program...
Funny, I think I've seen more than that in Vegas. right.
Well, but do you know they were Elvis? Anyway, so here's the deal. I think we do live in a mono-Elvistic universe, and here's how we ensure that. We have a public static final Elvis called Elvis, and we initialize it to a new Elvis with a private constructor. So that's the standard singleton pattern. And then what we do is we keep track of whether Elvis is living or dead. It turns out that the tabloids care about this. I don't know why. So what our program does is it simply prints out Hound Dog if the king is alive, and Heartbreak Hotel if he breathes no more. So tell me, Bill, which is it, Hound Dog or Heartbreak Hotel?
All right. So this is going to get our constructor. So this is the main method. We have to see if he lives. And lives returns the value of alive. Alive is a variable that is initialized to living. And living is initialized to true. And this one is trinary operators. Always have to double look at those when you do those. But this evaluates to true. So Hound Dog. Elvis lives.
Hound Dog. Okay. Well, let's see if, I'm sure that is one of your options, since there's only two sensible options here. We got Hound Dog, Heartbreak Hotel. It varies from run to run, or the ever popular none of the above. Let's give the audience a moment to think about this one.
I hear more muttering on this one than on some of the others.
Yeah. Now, when the muttering stops, we'll ask. I see Dick smiling. I think he got it.
I'm not sure. I was smiling.
All right, I think we're ready.
Ready? Is everybody ready? Time is up. The pens are down. Whoa! Oh, well. I spoiled that one. I apologize. Shall we?
How many people think the answer is A?
Okay. So since I spoiled it, shall we just go on? Fine. Okay. The correct answer is D, none of the above. It always throws a null pointer exception, and I apologize that I didn't give you an opportunity to vote. So, as for the intuition, class initialization is a tricky business, and auto unboxing happens when you least expect it. So let's take another look at this one.
How did null get in there?
How did null get in there? It's a very good question. So here's the deal. First of all, the initialization of this program is less than perfect. When you're looking at these things which involve class initialization, you have to remember that class initialization proceeds top to bottom. And the only way to figure out what the program does is to basically simulate it, to run it top to bottom. So what do we do here? First thing we do when we initialize Elvis is we create a new Elvis. Now, in order to create a new Elvis, we must initialize the Elvis class, but we're already initializing it. That's called recursive initialization. And does anyone know what the system does when you try to do recursive initialization? Shout it out.
Ignores it.
It ignores it. That's exactly right. It says, oh, gee, we're already trying to initialize it. We don't want to go into an infinite regress. So we'll just barrel through and create the new Elvis, which runs the sole constructor.
But that's empty.
It is empty, which means all it does is it does the initialization of all of the instance fields for Elvis. So where are the instance fields? Well, we've got one. We have alive, and it is set to the value of living. And what is the value of living?
Oh, true.
No. You know, it says private static final Boolean living equals true. So you might think it's a constant, true and always true. It turns out not to be a compile time constant, and here's why. It's because it's a capital B Boolean. That's an object reference. It turns out that except for strings, object references are never actually compile time constants. So this variable is a final. That means once it is initialized, it cannot change. But it turns out that in order to initialize it, you actually have to execute this line of code. And before it is executed, the value of living is not true, but null. You see this little true? It actually gets auto-boxed into the capital B Boolean true, a wrapped true. But before this line executes, it is null. So in particular, when we're executing this line, initializing the alive field of the So Elvis instance, we copy living, which is at that point null, into alive. So now alive is null, and it's final. It's never going to get changed. It will stay null forever. Then the constructor returns, and we finish initializing the class. So the next thing we do is we set living to true, but it's too late. We've already used it. We've already copied it into the instance variable, so it is of no help to us. And that's it for the class initialization. Then we run the main method. So the first thing we do is we execute this trinary operator, Elvis lives, question mark, Hound Dog, Heartbreak Hotel. Well, what is the value of Elvis?
The one and only.
Null. And there is only one null, by the way, so I guess in a sense it's...
Well, the value of Elvis is Elvis, but Elvis.lives is not.
I'm sorry, yes, Elvis.lives is null. I made this mistake last time as well. Elvis.lives returns null. And then we have to turn this null into a Boolean. Right?
Little b Boolean.
Little b Boolean. And in order to do that, we have to unbox it. And what happens when you unbox null? Null pointer exception. That's called a surprise left jab while auto unboxing. That's the problem here. So, how do we fix it? Well, what we do is if we create the singleton after we've initialized the field upon which it depends, so all I've done is sort of swapped these two lines around, then we fix the problem. We haven't done away with the recursive initialization, but it's okay because by the time we do the recursive initialization, we have already assigned a value to living, and alive takes on that value, which is true, and so it prints out Hound Dog, just as Bill said it would. But there's a better way to fix it. Why are we using these nasty capital B Booleans? Let's not, right? If we simply use lowercase b Booleans, that is the primitive Booleans, then the behavior of the program is much more predictable and, generally speaking, it'll run faster, if not this program, a program that uses a lot of them. So you don't want to use those wrapped values unless you have to. Now, I've actually kept the order the same of the initialization of the living field and of the Elvis instance, but it turns out it's no longer necessary. Even if you swap them, it would still do the right thing because of the fact that living is now a true compile time constant, whose value happens to be true. And what can we learn from this one? Well, wrapped primitives aren't primitives. So autoboxing blurs but does not erase the distinction between primitives and object references. Capital true is not, Boolean.true is not the same thing as true. You should prefer primitives to wrapped values because auto unboxing can occur when you least expect it. And it can and often does cause null pointer exceptions. So one thing you should never do is never use Boolean as a capital E Boolean, I should say, as a return value from a method to allow 3 possible values, true, false, or I don't know. That's just a prescription for disaster, because if someone then just does an if statement that takes the return value from that method, that if statement will blow up whenever it returns null. And it turns out, by the way, that there is at least one method in the JDK, unfortunately, that does this. The problem is the method predates the introduction of autoboxing into the language. And before autoboxing, it may not have been a great idea, but it wasn't a terrible idea. Now it's a terrible idea. So never use capital B Boolean as a 3-valued return. Also, watch out for circularities in class initialization. You can't avoid them. They do occur in a whole bunch of common patterns like singleton and type safe enum and so forth. But when you have one, you should make sure that you've initialized all the fields that you depend on before you use them.
All right, well, that was a good puzzle with a good moral. Now I have one for you. Mind the gap. So we're going to write out a file, and then we're going to read it back in, skipping over everything but the first and last byte, and see what the first and last byte were. And the question is, what does this program print?
This is a long program, but it doesn't look like a hard program. There's nothing object-oriented about it. Let's just go over it. So the first thing we do is we set gap size to 10 times 1024, that is 10K, and I see it as a private static final int, not integer. So this is a true compile time constant, which means it's just going to get replaced by the value 10K wherever it's used. So let's find out where we use it. We set temp to create a file whose name is gap.txt, and I think it throws some numbers in there.
This will create a random sort of name that's not being used.
Okay, a random name that's not being used. So we get ourselves a file in a good temp sort of area. And then we get a file output stream on that temp. And we write to the file output stream the byte 1. I guess that's an ASCII control A. Is that right?
Yeah.
Okay.
It's not ASCII, this is bytes.
Well, yeah, I guess, but you're writing to a file system, so it's, I don't know. Anyway, it's the byte 1.
Yes.
And then we write a bunch of bytes, in fact, 10 kilobytes of zeros, because we create an array of length 10K, which is initially empty. So we write all these zeros. Then we write 2. That would be a control B, correct?
Yes.
And we close the file. And then we open, a buffered input stream of a file input stream on the same name. And that's good, because I know you don't get buffering for free. So if you want to have buffered I/O, which you do, you do this wrapping thing. I guess that's the decorator pattern, right?
Yes.
And we read the first byte into an int. And then we skip the size of the gap, which is 10K. We read the last byte. Presumably this is 2, this is 1. And finally we print first plus last. So that's 1 plus 2, which was 3 last time I checked.
Is that your answer?
It's my final answer. 3.
All right, let's see if that's one of the options. Okay, so question is, what does this program print? Now actually one thing, we're actually dealing with the file system here. Right? And so to avoid any questions, I'm actually going to promise you that there are no issues with the file system. Nobody else touches the file doesn't go away, we don't run out of space on the disk, there are no I/O exceptions. Really the question is, reading and writing the file works just as you would expect, and the question is, what does this program print?
That's right generous of you, Bill.
Yes. I'm a generous person.
Okay.
So the question is, does it print 0, 1, 3, or it varies from run to run? Okay. Moment.
Looks like they're ready.
I don't hear a lot of muttering. So yes, now keep your hands off that button. All right. So
Make
the question
one mistake and you pay for it all your life.
All right. So how many people think that the answer is A, 0? A smattering. How many people think that the answer is B, 1? Fair number. How many people think that the answer is C, 3? How many people think that the answer is D, it varies? I think there were a few people sitting on their hands, but I think maybe D1?
Yeah, I think by a hair.
All right.
Let us find out what the program actually does. Now can I press the button?
Now you can press the button.
Okay.
Okay. In practice, it will print 1. In theory, it will vary from run to run.
1? Why will it print 1?
The problem is that the skip method returns the number of bytes that it skipped. It may decide on a whim to not skip the full number of bytes you requested.
Wait, let me take a look at this. Why would it do that? It doesn't make any sense.
Well, that's what the API says. It doesn't necessarily have to make sense. So the skip method, as I said, is declared that it can decide to just return any value less than, between 0 and the number of bytes you requested.
And you said it always returns 1 as a practical matter? Why would it do such a thing?
So it turns out that a buffered input stream, if there's already some data buffered, it will only skip the amount that's buffered and won't go down to the underlying stream to try to skip additional bytes.
That's ridiculous.
And so as a result, yes, and as a result, this will always perform a short skip. And thus, this read of last won't actually be the last byte in the file, but rather a byte in the middle of the file, which will be 0. And thus, first will be 1, and last shall be 0. And thus, we will print 1.
Ouch! So how do you fix it?
All right. Well, it turns out there's not a one-line fix. And in fact, a lot of times when you find yourself having to do something more than a one-line fix, the best thing to do is don't try to do it in place, but compartmentalize it. Define your own method. And so here we're going to define a method called skip fully that will in fact skip all the bytes you requested to. It will never return a short number of bytes. And if for some reason it gets back that it skipped 0 bytes, it will throw an end of file exception, because that is the one place where skip is documented that if you're at the end of file, skip will return 0. That's the only way to find out that you're at the end of file when you're using skip. It won't throw an exception. And so this method will always skip. It'll either skip the number of bytes you've requested, or it will throw end of file exception. And
Can you show me how it works?
Yep. Let's take a look at that. And once you've written this, next slide.
Well, you can't show me how it works if I switch to the next slide. I want to know how this method works. I don't believe it works.
Sorry. How this method works. Sorry. All right. So we take in the number of bytes that we've been requested to skip, and then we're simply going to have a loop. You know, how many bytes left do we need to skip? And so I call skip, and I've asked skip this many bytes, please, please, please. And it's going to return some value, right? If it returns 0, then although the spec doesn't say that that only happens under end of file, there's no other logical situation which you do it. So
and
we're going to
assume they've promised me that they're going to change the spec so that it does say that.
So that if this returns 0, then we must be at end of file, and we'll throw an end of file exception. Otherwise, well, we requested this many bytes. We're going to decrement it by the number of bytes we actually skipped, and then we're in a while loop. If we actually skipped as many bytes as we requested, remaining will be 0, and we'll be out of the loop and the method returns. If we didn't skip as many bytes as we requested, we go back for another skip.
So I believe that works, but it's a royal pain.
Yes.
And what can we learn from it?
So the skip method is hard to use and error prone. You roll your own skip fully method. Right? If you need to use skip, right, there's a request for enhancement to add it to input stream. Some few other things we're trying to do with Sun on this. In general, if you have an API which is broken, and there are APIs that are broken. The problem is once you make an API, it's cast in stone. It's forever, right? And if you're stuck with a forever broken API, come up with a better way to call it rather than persisting with the old use. And for API designers, don't violate the principle of least astonishment, right? I mean, make it easy to do the simple things. I mean, I find it hard to so interesting story about skip. There are 63 places in the JDK where skip is called, and in 56 of them, they ignore the return value, right?
So that behavior is so astonishing that even the people who wrote it don't believe it.
Right. And I think also pretty clearly the people who wrote that API never actually tried writing any code that uses it. Because if they had actually written anything more than a simple test case that used it, they would have found out, gee, this is really hard to use correctly. Why don't we redesign the API?
So the operative phrase here is use cases. The way to find out if your API violates the principle of least astonishment is try and use it. If you haven't tried to use your API, it doesn't work.
All right.
Okay, well that was a fine problem. Now I have one for you. This one we call histogram mystery. It almost rhymes. So, what we do in this program is we have a list of words. The words are I recommend Polygiene lubricants.
You do?
I do. And what we do is we make a histogram out of these words. The histogram is of length 5, and the way we make the histogram is we iterate over all the word pairs. So we have a doubly nested loop of words, and we pair the words together, compute their hash code, choose a bucket based on the hash code, and increment that bucket. Then when we're all done, we add up the contents of the histogram, and we print it out. So I want to know, Bill, what the program prints.
All right. So let's see, I recommend Polygiene lubricants. There are 4 of them, doubly nested loops, so there are a total of 16 pairs, including like, I, recommend, so forth. And for each one, we take the hash code of it, take the absolute value, so we get something non-negative.
Just to interject here, Bill, word 1 plus word 2 is concatenates the two. So we're just concatenating the strings.
Right. So we concatenate the strings, take the hash code, take the absolute value, and then we take that and mod the histogram length. So this will give us a number between 0 and 4, and then we increment the appropriate bucket. Okay. Now, at the end of doing this, I have like no idea how big histogram sub 0 is, but I don't need to know.
No, you don't.
Because all we're going to do at the end is we're going to go through and we're going to sum up all the values that are in any of the buckets. Right? So pair count is 0, and I go through and I sum up anything that got added. So I don't know exactly where each pair wound up, but since there are 16 combinations, each combination incremented 1 bucket. When I add up all the buckets, I should get 16. And do this. So I say this prints out C16.
C16. Well, that's a reasonable guess. Let's see if it's one of the options.
It is
Let's
indeed.
see. Your options are A, 83, B, C16, C, S, and D, none of the above. And I should mention, for those of you who are too young to have dealt with ASCII directly, that capital A is a 65 decimal in ASCII. I'm not saying this is necessary to solve the problem, but if you find it useful, go ahead. We'll give them a moment. This one's tricky.
It is. Looks straightforward to me. All right, I think we should move along.
Okay. I don't. They're still
right.
chattering. And
All right,
we
one
don't
more.
have a hard stop.
Okay, we'd run along. That's good. No little red buzzer like there was at Java 1?
No.
All right.
And they can edit these things out of the video. Nobody wants to hear you chattering. I'm sorry. It's nice chattering. But... Okay, the chattering seems to have died down, so I think everyone knows the correct answer.
Now, keep your hands off. So how many people think that the answer is A, 83?
We've got about a
Everybody's
third.
required to vote for something.
How many people think choice B, C16? Only one? Poor lonely Bill.
I'm unique.
I'll join Bill. Moral support.
Thank you.
How many people go with choice C?
Yes.
Okay, we got another third of you. And how many people go with choice D? None of the above. Smattering. So some of you aren't voting. But anyway, it seems to be a tie between choices A and C. Is that right?
Yeah.
Yeah. Okay. Let's find out what this program really does, shall we?
All right.
None of the above. It always throws array out of bounds exception.
How'd that happen?
Well, the intuition is that math.abs does not necessarily return a non-negative value, I should say. Absolute value can, in fact, be negative under certain circumstances. And it turns out that the mod operator, that doesn't necessarily return non-negative values either.
Oh, well, let's see this.
Let's take another look. See, these words were chosen very, very carefully. Now, it turns out that the hash code of the word polygene lubricants is integer.min value. And that the
And what's special about integer.min value?
Well, it turns out that the absolute value of integer.min value is integer.min value.
Well, but that's negative.
It is negative. So here's what's going on. In the 2's complement arithmetic, there are more negative numbers than positive. The idea is that you have an even number of values, right? You have 2 to the 32 int values. One of them is reserved for 0. That leaves you an odd number of values. So roughly half are negative and half are positive. But there's one negative number without a partner, and that's integer.min value. And if you apply the standard algorithm for negating it, it's the binary representation is a 1 in the high order bit and 0s in all the other bits. So to negate it, first you complement it. So you got a 0 here and all 1s, and then you add 1 to it, and you end up with all 0s and a 1. You're back where you started. Negative integer.min value is integer.min min value. And absolute value, if it finds a negative number, it returns its negative. So in every case but one, it does return a non-negative value. But if we pass an integer.min value, you get out integer.min value. And then we take it mod histogram.length. Well, the histogram length is 5. So you got a negative power of 2 mod 5. What does it return? It's guaranteed to be a negative number because it isn't 0, right? A power of 2 is not divisible by 5. And it turns out that division in Java always returns something, if it's non-zero, whose sign is the same as the numerator, which in this case is negative. It turns out, as a practical matter, it returns negative 3. And by the way, it always returns negative 3 because the hash code of string is precisely specified in the spec. So we get bucket minus 3, and we tried to add 1 to bucket minus 3, and there's your array out of bounds exception. So it never even gets down here. It turns out there is another little trick down here. It does not print out C16 because it turns out what we're doing here is we are adding a character value to an int value. And what happens is they're both integral types. So when you're adding two things of integral types, you do what's called the primitive widening conversion. You turn the smaller one, the character C, into the type of the bigger one, integer. So we do turn C into an integer. And as I said, A is 65, C is 2 more than A, so it's 67. So we add 67 and 16, getting 83. So the program, would print out 83 if in fact it didn't have this problem.
We talked about that in the first puzzle, didn't we?
We did. So how do we fix it? Well, two things. First of all, we do the absolute value after the mod operator, right? If the first thing that we do is we take the hash code mod length, that gives us a value between negative 4 and positive 4, right? If we take any value, whether negative or positive, mod 5, the result is going to be between negative 4 and positive 4. And by the way, 0 occurs with twice the likelihood of any of the other values, roughly speaking. And then we take the absolute value of that. If you take the absolute value of something between negative 4 and 4, you get something between 0 and 4. So now we are guaranteed to get an actual array location. And now the program does end up with 16 as pair count. And notice I've also changed C from a character to a string. So now it really will print out C16, just as my brother said it should.
Okay.
There you have it. And what can we learn from this one? Well, math.abs doesn't guarantee a non-negative value. Integer.min value equals negative itself.
Well, but that program was probably okay. It only goes wrong once every 4 billion times. I'm sure it would never go wrong while we're showing our software to the VC.
No, it wouldn't go wrong then. Nor I think after we sold it to an important customer, it would never blow up, for them. It would blow up when we were testing it, right?
If we do good tests.
Yeah, and this thing which everyone calls the mod operator, it isn't. It's the remainder operator, and it is defined to have the sign of the numerator, of the first number, the left operand, if it is non-zero. And finally, when you are faced with this problem of translating a signed hash value to a bucket, that is, an array index, you can do any one of these 4 things. Either you can do the remainder operator before you take the absolute value, as we did when we fixed the program, or you can right shift the number 1, effectively throwing away the leftmost bit, or you can mask it, effectively throwing away the rightmost bit. I said that backwards. First one throws away the high order bit. The second one, I should have just said high order. This one throws away the low order bit. This one throws away the high order bit.
Yes.
Right?
Correct.
And finally, if you use a power of 2 length array, you can simply look at the low order bits of the hash code, which is good if you are, believe that your hash code to be of high enough quality that the low order bits contain enough entropy. So that's it.
All right. So now I have one for you. A sea of troubles. And we're going to create a random number. Right? Well, actually, a random Boolean. And we're going to ask whether to be or not to be.
That is the question.
Yes, it is. And based on that, we're either going to get the integer 3 or a floating 1 and print out the result.
Well, this looks utterly straightforward. We get a random number generator. It's seeded with time, so who knows what it's going to do. We get the next Boolean, and I know, although this is a capital B Boolean, that it actually returns a primitive, so there's no boxing nonsense. So 2b is going to be either true or false. So it's going to be either true or false or true. Either way, one of them's got to be true. So once you OR the two together, this is going to be true, which means that we're always going to end up with the left side, which is the integer 3. So when we print it out, it's going to print 3, right?
Well, that sounds like a reasonable option. Let's see. Yes, indeed it is. So the question is, does this program print 3, 1.0, throw an exception, or none of the above? Put on your thinking caps. You know, sometimes he's right.
Rarely. I was right once before.
You are. It may set a record. All right, I think we're ready to poll the audience.
Okay.
So how many people think that this program prints 3? Raise your hands. All right. How many people think that this program prints 1.0? No takers on that one. How many people think that it throws an exception? Be proud.
Be proud. I see these tentative. What is this? Is this?
You're allowed to be wrong. It's okay.
I'm wrong and I'm right.
Right.
Okay.
And how many people think that the answer is D, none of the above? I think D won.
No, I think it was a tie between A and D.
Okay. All right, well, let's see what the answer is in fact. It prints 3.0.
3.0?
Yes.
That wasn't even in the program.
Yes, and the problem is that ternary operator has very strange behavior when operating with mismatched integral wrap types.
Let's take a look at the program again here.
Okay. So the problem is here we have a integer object, and here we have a float object.
But they're both object references. What's the problem?
Well, the problem is it's going to take so this will evaluate to true, right? No surprises with what's going on with the Boolean object. But it's actually the result of this operation is that it is going to create a float object containing the value 3.
So why does it do that?
That's why. It turns out that it's not, because it's a wrapped primitive type, it's not actually doing what it would do if it was simply an object reference, where it simply chooses either this pointer value or this pointer value. It's doing what it would do if you had a question mark colon with an int and a float, where it says, okay, let me take these two numeric types and convert them to whatever type is more general than both of them.
Now, I have an observation. This thing here, it looks like a car rental contract.
Yes.
And nobody ever reads those.
Yes.
So how do we fix this?
Okay. Well, one way to do it is to avoid the ternary operator, right? The ternary operator has a number of nasty corner cases. If you think you are not sure what the ternary operator does in a particular case, don't use it. So here we simply declare a value of type result, and we use an if statement, and either assign to it a new integer or a new float, and in this case, we will get the integer object 3, which prints as 3.
Okay, and what can we learn from it?
Okay, so avoid mixing types. The question mark colon operator has counterintuitive semantics when used with two different wrapper types, and if you must select between two different wrapped integral types, use else if rather than the question mark colon operator.
Now, I should point out, by the way, that the question mark colon operator has sort of gotten a bad rap. It is very useful when it is being used on two objects of the same type. So feel free to use it under those circumstances. It's just these odd mixtures of wrapper types where it really screws up. Okay, so that was a fine problem. I have one last problem for you, the last problem of the day. Is that a sigh of relief that I hear? This one we call ground round. And the reason we call it that is because it involves the round operator, math.round. All we do is we generate a random integer, and if the rounded value of that integer is unequal to the integer itself, we print ground round. So what I want to know is, what does this program do most of the time? How does it behave?
All right, so we create a random number generator. We get an int value from it, and you take an int value and you round it and round to an integer value, and you ask, is that not equal to an integer? I mean, round takes a number and moves it to the nearest integer, and last time I checked, the nearest integer to an integer was itself. And so you should get back the same integer. This should be the identity function on ints. And so it should never print ground round.
Never. Let's see if that's an option. The options are never, seldom, almost every time it's run, and every time it's run. So what do you think? Does this program never print ground round? That would be choice A. I thought
Are we ready to vote?
I think we're ready to vote. Are we? Yeah, I hear some chattering. We'll give them a moment.
I think most of them have reached a conclusion.
We'll give them a few more seconds. This is the last puzzle of the day. So.
Yes. Last one we present.
Good point.
They have the whole afternoon. Okay, I think we're ready.
Let's give them 10 seconds.
All right.
All right. I don't know, we got about a few of you. And how many people say D every time it's run? A smattering, almost no one. So the winner, I guess, is seldom? Is that right?
Yeah.
Seldom. Okay, time to reveal the answer. The answer is, in fact, almost every time it's run, 97% for those of you who are obsessed with quantification. It turns out, the intuition here is that there is a silent, lossy conversion from int to float, and that, in combination with the fact that math.round of float is the method that is invoked, is killing us. So let's take another look at it. See, the problem here is when we call math.round of I an integer, there is no method defined in math called round that takes an argument whose type is integer. There are two versions of this, two overloadings defined, round of float and round of double. And the float one is the one that gets invoked. And that is true because whenever you have two applicable methods, it chooses the most specific. So is every float a double or is every double a float? Every float value is a double value, and that makes float the most specific one. So this is the one that gets invoked. Now, in order to call round a float on an integer, you have to convert the int to a float. That is called a primitive widening conversion, but it isn't really a widening conversion. It loses precision. You have 32 bits for an int and 32 bits for a float. Well, 8 of the bits in the float are used to represent the exponent. You can represent huge values with a float and tiny values, and that means you do not have one value left for every integer. So some integers must end up with the same float value. By the time you've converted the int to a float, you've already lost. So how many of them do you lose? Well, as I said, there are 8 exponent bits. There are 256 possible values of those 8 bits. So that means, you know, that roughly speaking, you're going to lose sort of 99% of them. It turns out it's not quite 99%, and to understand why, you actually have to go into the details of floating point representation, and we don't have time for that today. But because of that, virtually no ints, when converted to float and then converted back to int, are equal to themselves.
Statistically speaking.
Statistically speaking.
You know, 0 through 10 are okay.
0 through 10 are okay. The low ones are okay. It's when you start getting high that you start really, you know, losing big time. So how do we fix it? Well, if we cast I to a double, then we end up invoking the version of math.round where every int has a unique value, because there are only 32 bits in an int and 64 in a double. So by converting an int to a double, if we convert it back to an int, we'll end up where we started. And what can we learn from it? That silent, so-called widening conversion from int to float is both lossy and dangerous. It was a mistake in the language design. You know, basically, you should never get a conversion where you lose precision and not get a warning or even an error. you should have to explicitly cast to get from int to float, but unfortunately you don't. More generally, the float type is seldom called for, as my brother said earlier. Unless you have a huge array of the things, don't use float, use double. Double is better. In this case, you weren't really choosing to use float, but you were sort of getting it shoved down your throat. And finally, method overloading is dangerous. Arguably what killed us is that there were 2 overloadings of round. If if they'd given them different names, or if there had been no version of it for float or something, we wouldn't have ended up in this nasty situation. And that brings the normal part of our talk to an end. So now we have the abnormal part. Java is a reasonably simple and elegant platform. I used to say it is simple and elegant, but I think as of Java 5, I can't call it that anymore. It has gotten a lot more complex, it has a few sharp corners, and you should learn to avoid them. And if someone wants to make it more complex, you should think very hard about whether that is something you really want to do to the language.
I mean, I will mention that we had to work long and hard to come up with these puzzlers.
It is true. It used to be easy to find puzzles that we haven't presented yet. It's gotten much more difficult because we've sort of mined them all. And unless we make the language more complex, I'm afraid we're not going to get a lot more fundamentally new puzzles. But here's a good rule. If you aren't sure what a program does, it probably doesn't do what you want. Keep your program simple and you will stay out of trouble.
Another important thing is to use FindBugs. It's a static analysis tool that I've written. It's actually used within Google, available through BugBot and very shortly through Mondrian. And it actually finds all 8 of the puzzlers that we discussed today. If you enter those codes, FindBugs will say, hey, you're making this kind of mistake, fix your code.
And for our viewers on the web, where should you go to find the bugs?
Well, you can just Google FindBugs, and it will take you to the right location.
Excellent. And finally, don't code like my brother.
Don't code like my brother.
And now, a word from our sponsors.
If you enjoyed this talk, then you should get a copy of this fine book called Java Puzzlers by myself and Neil Gafter. It contains 95 puzzles, none of which we presented today. So there are 95 different puzzles, 52 optical illusions, and tons of fun. And in case you wonder what this is here, this is a shameless plug. Yeah. And that brings to a conclusion our talk. So thank you for coming. And thank you for staying.
And I think now we can take some questions.
So how long did it take you to find a string
Excellent question. So the question was, how long did it take me to find a string whose hash value was integer.min value, and that made sense. So I have a dual processor Opteron 170 at home, and I unleashed it. I have a dictionary of 200,000 words, which means there are 40 billion word pairs, and I unleashed the Opteron on that, and it took it 10 minutes to calculate all the hash values of every word pair. It found 11 collisions, and this was the most amusing one.
In your 2-unit example, where you catch error and exception, if some of the code inside of the thread had died by throwing a throwable, would you have, would that have not just...
We wouldn't have caught that, yes.
So to repeat the question, if in our JUnit example, the code had died by throwing a throwable that was neither an exception nor an error, would it have not caught it? And the answer is yes, it would not have caught it.
Don't
However,
do that.
Yeah, don't do that.
I mean,
If it hurts when you go like that,
don't do it. Yes, the language.
Things up there are things you should don't do as well.
Well, but but it's a rule. I mean, the language would allow you to define things that are neither an exception nor an error. I think there's absolutely no use case for that. The language should have forbidden it.
I agree with my brother in this instance.
Yes. Back.
Is there any reason that math around the role
Again?
So the question is, should we define a math.round that takes an int value? So I had one suggestion for how to fix the problem in ground round. That we could declare a function in math called round that takes an int, returns an int, it would be the identity function, and we would deprecate that function from the moment we added it. Right? So if you ever use that, I mean, because there's no sense in calling that method. And so if you did it, you would get, rather than getting the float version, which is lossy, you would get the int-to-int version, which is marked as deprecated. And that would be one reasonable thing to do. And you know, one of the things which is often interesting is you find yourself with a mistake in an API And they say, well, we can't actually fix it because that would be incompatible. And then you try to figure out, well, is there some way that we can tweak things to make it be not so troublesome? And that might be one way how you could do something like that.
Yeah, although it is arguably not upward compatible. You're changing the behavior of existing programs. I would say a better solution is to run FindBugs. Now, there's something my brother did not say because he was too modest, but I will say it. FindBugs catches all 8 problems in this year's talk. If you simply run these things through FindBugs, it will draw your attention to every single one of them. So just run FindBugs, and that'll take care of this one. Yeah?
What if you were to use Rint and then just cast the integer? There's not, I think there's a method.rint, which just rounds to the double value that is equal to the integer value or something like that.
If there is, I've never heard of it, and I don't have time to check right now if it exists.
We can check offline.
But the problem, remains that if you do the obvious thing, you get hurt. So this is a case where, it definitely does represent a trap or pitfall.
Well, the problem is that nobody is probably going to, deliberately invoke the round function passing it an int. Sometimes we've seen cases where people will do a computation and they think they're getting a float or a double, but they're not. They're actually getting an int, and they're accidentally doing the silent lossy conversion, right? This was a contrived example. Many of the puzzlers are. But the important lesson is this accidental lossy conversion.
Yeah.
Isn't that actually fairly likely to happen with generics? And is there a push to fill out all the signatures of the library so that it's less likely to happen?
Is that more likely to happen with generics?
I don't know if this is more. The question was, is it more likely to happen with generics? Is there any solution? I don't know if this one is. It is the case that generics, especially in conjunction with autoboxing, auto-unboxing, and varargs, complicates enormously the overload resolution algorithm. So it does make it more likely that you will invoke the incorrect overloading. I think the only solution there is added care, especially added care in API designs. API designs that used to be reasonable are no longer. It is even less advisable to use method overloading than it used to be, and static analysis tools can help you find potential problems in pre-existing APIs.
I don't actually think that this would be a problem because the generics is done by type erasure, and you can't do something where, you define something that's generic over numbers, and if you actually give it int, you invoke this overloaded version of the number.
This one wouldn't, but other ones would. We do have other puzzles that rely on exactly that.
Right.
For example, in list, there's a list.get method that takes an int. Well, if you have, and list.remove, that removes the ith element. If you have a list of integers, you now have this funny overload resolution problem where if you remove 14, are you removing the number 14 or the 14th element? It turns out it's the 14th element, and that's very confusing. So, any other questions? If not, thanks again for coming. Thanks again for staying, and see you next year.